The second you made a sound.
Shit. Oh, sorry. Okay, so and we have people online.
There's Kanai.
There was.
There's Kanai.
Nice. There for coming.
Good.
And he's gone.
So it is about layout consideration. I'm going to so it's not like a teaching or a presentation. So but just it is like I'm going to through some of the techniques and consideration for layouts. Okay, then we can comment, and it's like interactive talk. Not interactive talk, it's interactive meeting mostly. So okay, so I'm going to start with the one of the techniques that everyone knows is to use wire. Do you use wire for your when you are going to connect your source and drain? Do you use wire?
Bias and wire, yes.
Wires? You use them? How many wires do you use?
On vias, normally it's 1 or 2 vias, and like it's all about the space you've got. Normally, I only use 1 or 2 to clear the DRC of minimal metal area.
Okay, so you're going to this is the gate, this is the one of the source or drain, and this is source or source drain. So use wire, like one wire.
The vias, it always depends on the length of the
Yeah.
of the old thing. Normally, I just take a via, rectangle via, and just put it all over
Yeah.
it, all over the source, all over the drain.
So this is a very good comment. So we should use always like a big wire, not big wire, lots of wires, so because of the RC and everything.
But it depends also on the space you have. For example, if you have a multi-finger transistor, you
Yeah.
have to connect the source and the drain, so we use the half of the space. But depending on the current, this transistor, is it just an inverter, or, for example, a big LDU, a fast transistor for LDU?
I do not know the correlation between wire and space, because the space is already there and you just put wire on it.
But
It's like
how will you connect
Well,
the source?
if what I'm doing right now is to like this. If you have a multi-finger system, and you just if you add one other here,
it is another source.
another source, what I would normally do is just put all vias here, take my wire out, and wrap myself around here to get somewhere else. And do the same thing here.
Oh, not connecting all of them through the transistor.
It's just, I use the wire at the.
This is one way to do it. And you do
Like over the
this
transistor.
one, the drain here. This one.
But the effect is not on the spacing, it is mostly on maybe parasitic between the metals.
Yeah, I mean, because what I do is I use, for example, metal 2 for horizontal wires. So if you have your source is metal 1, you do metal 2 all over it, and you have another transistor here, we block your metal 2 with these wires.
Good. You put, but
But
okay.
what is the purpose of putting, of covering? all
Because
this with
when you
wires?
have something like a big one, Well, it's not.
Paint the one board. It's not paint is not going to be.
Like I said, for an LDU, for example, your transistor will pass milliamps of current. It's better to put your vias here. All the current will.
So what I understand from what you're saying is if you have the space, you're better to use a lot of vias.
Yeah.
And if you're really short in space, you just do the minimum vias that you could have while all
Yeah.
while putting the same voltage on all
If
of the.
this transistor, because we're talking about layouts, matching. If this transistor is just the switch,
Okay.
this is VDD, for example, and you have here VDD offloading no application. So you don't have here you have you don't have a current flowing, you don't have matching considerations.
But
You can
I do not.
only two vias.
I still do not see the point of why on matching.
Uh,
I'm talking a little kind of it is not working. Oh.
You can go to the whiteboard and draw offhand.
I really try for the I really what's the word for it? Like exercise for this. Why is it not working?
Because it's in the middle of a presentation.
Yep, that's.
It's always like this.
It's not
used to be
working.
okay.
No, that
that was your
that.
pad. And it's gone.
Use the pen on the trackpad.
But because it's going to be recorded, I'd like to do it. After it is working. I was going to say that. So when you have the transistor and this is the one, the source, and this is the drain, and you have not enough wire, so you have like a resistor in your source or drain. Okay, that's a lack of connectivity. So it's mostly is about the connectivity, not about the matching.
Yeah, true.
So, for example, if you you design something like this, common source, having a resistor over here is not a good idea.
But in some applications, it's not a problem.
Exactly, it's not so. I never use a lot of wire because
If you have a differential pair,
Mhm.
you should be sure to not put the resistor in both of the transistors.
Yeah, but it's not matching.
Yeah, it's not matching.
It's not matching. So sometimes, but mostly if you're in high frequency, it is good to use lots of wire because in high frequency everything is very susceptible. So, but I do not use lots of wire, and always it's not too much difference between the.
You should.
So the next thing is the one of
Maybe it depends on that. Lots of bias, it means
lots of parasitic.
lots of metal, lots of bias. If you have the ground passing
Yeah.
another metal, so
Does it also depend on the layout map? You are trying to say that.
that's not the same.
Another thing is merged transistor. Do you have any comment about merged transistor? You can, when you have a cascade, so this is M1 and this is M2, and they are big, maybe like with 10 to something big transistor, you can do the fingers, so it will be like two of them, and you should connect them with metals. We are doing that, all of us, but one way is to merge them. What is the merge? So this is, for example, this is S1, this is D1, and also this is S2, and this is D. Yeah, you are going to, this is the gates, okay? So you start from the bottom. It is S1, then the gate, then D1. And because in MOS technology, there is no difference between source and drain, so you use S2 over here. Then the gate for this one, and you use T2, 2. And then a gate, and then it will be S2. S2. Then the S2 is already D1. Then come back to the S1, and then come back to the top. It's like instead of layouting two big transistors, it's one transistors and as a cascade.
That way you can almost shrink
Too much.
a third of the size, because you only use,
Yeah,
since you share the drain and the source, you can shrink a lot of the size of the transistor.
Yeah. yeah. It is good for example, in 28 that we have, do you remember those big guys? And one of our approaches is to have a very dense, one of the thing that we brag about is having a very small and dense chip. So maybe this is a good idea also, but when you do this, the parasitic will change and also the threshold will change, but very little, not too much. So merged transistor isn't one thing that we can remember and use. I never use it because you should lay out the transistor by yourself. It's not like a P cell that you flick.
You can do it, instead of using fingers, you should make a player. And you put the finger to yourself, so the finger, one transistor, and then the second, and then the first.
Like what? Can you show us on the?
It's a cadence shenanigans.
It is a three finger.
Which graph?
I don't know, like, so this is your S1, U1, U1. You have this node.
Which will be overlapping with D1.
Yeah. You overlap it.
Oh, you can
You take
overlap it.
another finger on this one, you overlap it.
But when you overlap it, it will not be DRC problem.
No.
No.
We merge automatically. In case
If you have a gap, it will trigger. If it's overlapping, it will not.
Okay, that's
if
one.
you approach it, it will overlap.
But it's mostly like you should do it with your hands. It's not like a P cell. So yeah,
I do it every way, it's very fast.
it is very.
Okay,
yeah.
so you just
If
overlap.
you drag it, if you drop it here, it will overlap and it adjusts itself to the exact same.
Yeah, thank you very much. That's what we're.
If you're doing analogous system, even if you do your own cell, it just takes a little bit of time to start. But once you've made it once,
Yeah.
it's pretty easy to just
Yeah.
paste it everywhere. So
You can even instantiate the mosaic
Yeah.
array of cells.
Yeah.
And you calculate the gap, the pitch between the.
I always wondered when I,
The pitch to merge them? Reduce the pitch to merge them?
Yeah, you calculate the
Okay.
pitch, so they,
it's exactly the same thing with the thin and dim contact.
Mhm.
Well, normally when you mosaic them, there's always like 0.53 spacing, so there's a little gap that makes
Yeah.
a million DRC.
Yeah.
So you shrink it a little bit,
Yes.
just so for it to do that. I always wonder when I'm wiring, if passing in front of gates is a bad idea. So like you have your metal two, and you pass your metal over the gate. I always wonder if it is a really bad idea to do so because you make some capacitive.
Yeah, I think it's depend on the design. Yeah.
Maybe in high frequency.
Yeah, yeah, for example, in here, this one, if this is like something like that. So having a resistor over here, this is a bias, so who cares? But having having a transistor or capacitance over here is not a good idea. Here is not good, but here, who cares? This is just a bias.
But the capacitance,
It depends.
it depends, it's not
A rule of thumb is
that
don't,
big, it's,
it's a rule of thumb that you shouldn't do it, but if you're obligated to because you don't have the space,
Yeah.
if you do it wisely, you can do it.
if
Yeah.
your gate is 60 nanometers, for example, you have your wire 100 nanometer, so the capacitance is really small.
Yeah. But
Maybe in high frequency.
Yeah.
can-
in a high frequency, so you know, this small, it will be.
High frequency being from about which
Gigahertz.
range? Gigahertz, okay. Gigahertz or gigahertz?
Giga, tetra, something like that.
Tetra, it's not close.
In megahertz, I never seen a problem.
No, in low frequency, no.
So megahertz.
Yeah, yeah. Always,
But low gigahertz can start, or even then, it's really like when you're at 30 gigahertz, 60 and. Okay,
but it's like when you design something, it's like, they told you that this is for high frequency, so be careful, so
Yes,
you know,
okay.
you already know that.
But even with that, you have to study the effect of this bias.
Yeah.
Because we are always taking care of parasitics, but they are not as of the word, dangerous on as that of the design.
Yeah, yeah, yeah.
In
They
that,
are there.
in that configuration, how would you place your wires to account of the, like, the 3 places you get to connect?
Like in here,
Yeah, how would you place your wires?
like that, this one is this one. So,
D1
D1
and
is
D2
this one,
D1 you don't have to.
D1 will be here, but we have D2. No, we have. So this one, it will be D1, and then it will be
D2.
D2.
Yeah.
Yeah, it will be, no, it shouldn't be like this.
D1 and
S2, yeah, S2, so now we have.
D1 is 2.
Well, you'll have some wires overlapping others, as I understand.
Yeah.
Vias and the transistor.
Yeah, you will have,
Yeah, you have multiple layer of metal, so.
yeah,
Probably I do it like.
Messing with it. That
Yeah,
was my
messing with the
question, but since it's low frequency, it's okay.
yeah, well, I'm.
you do it like parallel. Not, yeah.
I have some DC shenanigans.
This
I
is
don't have it
insert
here.
two, and after that, so you have. You have another transistor here. You put here, like 3.
Yeah. Yeah. But it will be a problem, you know, the metal will be a problem.
Metal is a problem.
Yeah, overlap. Are we good here or go to the next one?
Could go to the next one.
Then, so the next one is the main part of the talk. So, this is one thing, it's not related to high frequency, low frequency. We already have this problem in the project that we are working on in 28, which is matching. We have always the problem of matching, mostly in something like this current mirrors. You have that, and mostly in differential pairs, they should be matched. And they will not be because of some effects that I'm going to talk about. So you should compensate for that. And the weird, not weird, but the annoying part is that you should compensate and cadence is not there for you. You should already know that there is a problem, so cadence will not understand this effect because those effects are for after fabrication, after tape out. So it's like tape out things, not design layout thing. You, everyone understand what I'm talking about?
Well, I don't know what the defects are from the tape out on the symmetry, but keep going and.
Yeah, sure. So we should understand this effect is not something that when we simulate, we find out that we kind of solve the problem. So it's after tape out thing
Depends on the,
on the effect, yeah, also it's
Yeah.
different.
you're talking about the well proximity.
Yeah,
The well proximity in post-layout simulation, you will see.
Impact.
if you told me that,
Mostly,
you told me that, and I find out this thing from a very famous guy that everyone knows. You know, this is the guy that everyone knows. So I mentioned that the LOD and other well proximity effect is not really anything to do with
The mismatch.
uh,
Talking about the mismatch.
yeah, the simulation. It's because the founder you found is effectively saying that
He's talking about the random mismatch.
uh,
But we have some effects, SA, SP, well proximity and everything. These are extracted during the
Oh.
extraction of the parasitics.
but my understanding,
simulate that.
my understanding is that it will not affect the mismatch because
He's talking about the random mismatch. If you have very small transistors, for example, for a differential there, during the fabrication, they can be different. If you have very big transistors, they are different a little bit, but they still have a good mismatch performance. So they are big, and that can be calculated or can be simulated with a Monte Carlo mismatch.
But you mean that well proximity is already something that that cadence understands?
The proximity SA, SB, it is the distance between the gate and the edge of the transistor.
I've seen a few things that are sensible to those, the size of this pad, but it's mostly on weird,
Okay.
excessively specific.
So what you are saying is right, you have to take this
Yeah.
into account when you are designing, but the simulator will help you solve some.
Okay, some of them, okay. So the first one, when you're going to lay out a differential is to lay out it in like horizontal or vertical. It shouldn't be, you know, it's because electron moves like that and that. So it shouldn't be something like this. This is not correct. It should be like this or like this. This is very important for differential pairs.
So as my understanding of the drawing is that each of the squares are one side of the differential pair.
No, yeah, this is the one transistor and this is another.
You can have multiple transistors for
Yeah.
each side. Put them
On this, you're talking,
A, B,
Yeah,
A, this way.
you're talking about the direction of the
electron.
currents and not the space, the specific space of the transistor, because I think it's concentrated that you just, your A and your B are not on the same X and Y, but it's because you have a bigger grid. And overall on the grid, you have an averaging that is about good. So you have A, B, and C, and you mismatch so that they're averaging the same thing, but the current will flow in all of them from left to right.
I don't understand this well. What would you put?
It's about two types of things. One, you have like the current should, like you said, pass always in the same direction. So if in one it passes from left to right, all of them should be from left to right. But on some type of, I think it's centrated. If you have a lot of things, you can just switch them around. So you won't have all your C's here. In some case, one you can have your C here and here. If you have two transistors that need to be the same, so you can just.
Yes.
But in all the case, the current goes
Yeah.
in this direction. It's just, you can put your transistor not exactly in the same,
Yeah.
but it's sometimes at the same X and Y axis, as long as the current flows in the same direction.
Yeah.
Is the current direction only on symmetric systems, important on symmetric systems like
Yes.
differential player?
I just one of them. I don't know about others.
Okay.
But
Because
for symmetry, important.
I was wondering for the merge transistor you were talking about, that the current goes from up to down,
Yeah.
then splits into left
Yeah.
and right directions.
It's not about that, yeah. For cascade is not important.
Okay.
They do not have any effect on each other, no. Helping each other. So it's important to, for example, doing in one of design, we did something like that. It was the A transistor, and that was the B, and it was something in between. Not okay, shouldn't be something in between. Should be
But why will you put them in vertical?
or horizontal.
Horizontal, you can merge them, can have,
It shouldn't be merged because they are differential pair. They
you
are,
can merge them on the,
but they're
they have a.
same source,
Same source, so you can merge them.
but you will not have matching symmetry, I suppose.
Can have.
How you can have that. But let's draw it. Okay, I think it's done. So
I missed a bit the point, désolé, j'étais avec Jean-Denis, là, pour le problème de cadence, là. So Maya, what you just said, is it, I just heard about merging and matching.
We were talking about the differential pair.
Yeah.
And I said, why would you put them in a vertical way, so one on top of the other? Generally, we put them next to each other, and we can merge the source, for example.
okay. I'm going to explore that. I think it will not be the same. So this is the S for both of them, and this is D1 and D2.
Okay.
So I'm going to start with S1. S1 will be also S2. So this is not
Put D1,
S2, okay.
S, D2.
So this one will be which one? D1 or D2?
D1 left, D2.
D1 left, D2 right.
For example.
Then you have then you have S2.
S, we can call it S. S1
Yeah.
and S. It's
It's the same.
And you can put D1 and then.
No, because from S2 you are going to D2, and from S1 you are going to D1. You cannot go from S1 to
But
D2.
electrically, it's the same node. I mean,
Yeah.
But one part is different. I know that.
it's
But
the,
if it's the same, we can do that. So I know I should put S1, and then it will be
D1, in this case.
And what about here? It will be
Depends how many gate, how many fingers. If you see so you can have a symmetric system.
Usually-
Yeah, go ahead, Connor.
Yeah. Malheureusement, is it possible to draw something with more? How can I? Okay, if I request control. Oh, okay, request control.
Give him the control.
Yes.
Like hello.
Okay, so can I draw? Est-ce que ça va marcher si je fais ça? Non, ok. Ok. Ah, c'est le pointeur de RH que je vois. Ok, c'est strange. Bon, peut-être je pourrais descendre rapidement ce point. But okay, what I wanted to say that usually for diff pair and for current source, the matching is very important. So what we used to do is that you will make a centered approach for that. It can be so you can have, I don't know if you can draw that. I cannot do anything. It doesn't draw anything. Okay. But it will be okay. Let's say if you call this one the device A and this one the device B, for example, so you can have a pattern, or maybe okay. I will open on my side band here and share my screen. That will be easier. Okay, and share screen and this one. Okay. So usually for a diff pair or a current source, those are usually the well-known structure that are very critical for matching. So if you are, let's say, we call this A and this one B, same here, A, B. Usually those for, let's say, even we talk about offset this morning, random offset. So usually those ones are big, and so there is a big number of multiply and so on. So usually you can split them in different parts. You can have one block. Let's say if this, je sais pas, je prends un exemple. Let's say this one, I just take an example. This one has 40 finger. This one 40 finger. You can split it in, let's say, in four parts and 4 parts here, and you can build one group and say, let's say A, this is having 10 finger. The side you can put B, you can put A again, and even okay, we can go okay in the other region here, and yeah, let's do it that way. Okay, B, and yeah, well, so you can do it. The only thing, okay, you can have a pattern being A, B, A, B. You just need to keep symmetry, and okay, in that case it will be let's say 20, 20, and 20, and 20 here. But at the end, you have a kind of matching and symmetry here because you have A, B, A, B. So usually for mismatch and so on during the fabrication process, you can have some gradient. For example, the doping gradient in that direction. You can have a gradient in any direction. In X, you can have gradient in that direction. You can have a gradient in that direction. This is why usually we use a centroid thing, so that this is the most perfect thing for matching. So that if you take the structure A and B from a center point, you should see exactly the same thing. Is it clear so far?
And I was going to talk about that, but here is.
Okay, okay.
This is the thing,
But-
now we are talking about why, if we merge two differential code, it will be matched or not. It will be in a symmetric way or not.
Okay, so if we stay here about the merging thing, so as Maya said, this can be merged because this net, the source here, for example, is common to both. So at this junction here, the source is there. You connect the source of, let's say, the last one here. So the internal source, yes, for this one. I mean, it's the same net. So anyway, it will be connected because at the end, you will have to use a metal to connect all the source together and all the source together, A and B. But at the junction here, this one S, let's say the device you will have, if I draw, let's say 1, 2, 3, let's say suppose you have 10 here. So the last part here, the source of this one, A device, is also the same source of this one, B device, and they are connected. I don't know if it was the discussion point you had, but there is no.
The connection is, but we are talking about if it will be symmetric or not. Is it the
If
question?
it will be symmetric,
Yeah. Can you show
yes,
I can
there is
show
no symmetrical
something.
issue here.
Yeah, I found the picture. It is. Yeah, this one. Can you
what should I?
just the
Oh,
Teams
yeah.
window?
Yeah.
So
You could enlarge it, the
How?
computer. Yes, thank you.
if you, as you see here, we have the gates.
The gates are the black one. The
So here it is the gate one. There are two gates of the first transistor, the A transistors. So it's 1, 2, 2, 2, 2, 1. It's
Exactly.
symmetric.
So yeah, so this is
How do you know
exactly
that
what I
those are
drawn, but with
symmetric?
a smaller number of device merge.
I know the connection is here.
If you look at it, it's symmetric in
It's not a matter of looking. You should. Well, What?
It is symmetry. It is.
no, so we should maybe we should go through what is symmetry. Like symmetry is not to be like symmetric. So,
I mean, okay, one of the.
let me draw some. Let me draw on the with the wall. So the symmetry is like when you have two transistors. So this is the source, this is the drain, and this is the gate. Okay. So what this one can see, the source, should be same as this one.
Okay.
So for example, in this case, those are not symmetric.
Yeah.
What you are going to see over here, it should be same as here, and here is for here. So symmetry is like the source and drain have everything like the element. What is that for? That implanting thing, implantation. Yeah.
So here in this case,
We are, this
we
is,
are using multiple fingers. So if you take the fingers in the middle, they are symmetric. You can see it.
no, we should find out source and drain, then we.
Okay.
So this is source one, for example.
It is this. The first one is gray one.
So this is drain one, M1. Okay.
Gray M1.
And this one is source one.
This is the common source. So source one.
Common
Source
source.
M1, source M2. It's the same. It's the.
Yeah. Well,
Yeah, the source is the. So these are the sources.
No, let's, no,
Well,
go one by one. By one.
the thing with the symmetry,
And you can see.
it isn't symmetric if you consider the fact that you have nothing on the other side of the device. But the reality is you probably have dummy on each side, so you have your symmetry there too. So the D1 will do the same thing as the D,
Yeah.
as the other side.
For, see, if we take this one, M2, and this one is M1. So they are,
So this is D1, this is,
D2
D2,
this is D2.
this is D2, this is,
source. In grades,
top one, is which one?
Source is.
So let's go through it one by one. D1,
This one,
yeah, D1.
it's D1.
Go.
Here we have to put a terminal.
No, let's go through, then find out that if the
Okay.
bridge transistor is symmetrical, go through it, like draw
Okay,
it. one by
this is
one.
D1,
Okay, then the next one,
next is D1. For the
next
Oh,
one,
this
what
is
is this?
source.
Write it down.
Did it?
Not here, the D1, okay, so what is this one?
Ah, comment, chouette, mais
Ok.
Yes.
savais-tu ce que c'était? C'est maintenant.
S again,
Yes.
D1,
D1,
S,
yes.
D2, S,
D1.
Yes.
D1, S, D2.
So,
Okay, what I was talking about, if you take M1 and M2, each one has a drain in the extremity.
in the void.
After that, for all the fingers, it's the same, it's symmetrical, it's perfectly symmetrical.
I'm going to find out, so S1, C, D1, and S, SC,
Yes,
one,
D1,
SC.
D2,
So S also, so this one also, this one, C, D2,
D1.
D1. So, I don't know. What about the balls? If you add the balls, it will not be on symmetry. So add it. Okay, so
We put
now,
your contacts.
now D1, the D1, this is D,
These are your contacts, so you have.
this is D2. D2 also see the ball, you won't see the ball.
Oh, it's not the point, we put the dummy here,
And then you have the other side too.
because of
Yeah, but,
the well proximity here, vector,
okay.
the LOT, the length of diffusion. But this one, it's doping, it's a gradient. Have to always put dummies, so you will have, so your dummy will be in the region of
Yeah,
decreasing.
Yeah. okay.
So this one is missing the dummies,
Yeah,
but it's,
if we continue.
and for the merging, this source, let's say the current is coming from the drain, go to the source. Current will like that, will go. There is no problem of having a common terminal for this S1 and S2.
Sure.
What you have to avoid is having, say, a transistor here,
You're talking about
another
them?
gap, and another one.
Yeah.
Because here you will have the effect of the edge, and they can be different, you can't control them.
Yeah, okay, I'm going to talk about that.
Thank you.
So it's the
Sharing.
no, yeah.
You're in the chair.
I'm not sharing with them, yeah?
Not anymore, everything else is under control.
Okay. I act like yeah, so okay, share.
It's
You're right.
It's like a leap button.
So what is the next one? The next one is shadow effect. So we are going to talk about the shadow effect. So what is shadow effect is the compensation for that is the same as wall proximity and everything. And the shadow effect is it's not important, it's a physics thing. So when they are fabricate the transistor, it will be, for example, these are two transistors and they are going to implant the source and drains. So this is source, this is drain, source, drain, but they cannot do it like this. Okay, it's going to be a little tilt. Yeah. So I'm going to exaggerate here. Okay, so it will be like here, we have lots of good implementation. So here, not too much good. Here, good. Here, not too much good. So you are at dummies to compensate for that. So dummies will be like source and drain. Dummies. And in the same distance, everything.
So we will have bad implantation everywhere.
Yeah.
Of course.
Yeah, so this one also, the source will see the same thing that this one sees, bad implantation, and this one is also a bad, a good one.
I think it's also the effect of transistor, one of the middle transistor and the other, so. Since you have a transistor in the way, the second drain wouldn't be as good as the first if they weren't transistor on the side.
Yeah,
It's not just the source is worse than the drain, it's also the second drain would be worse than the first.
and you cannot control the problem with this effect. You just add something that this one C space a good thing. This one C good thing too. It's just, but you cannot control this tiling. They call it tiling, I suppose. Tilt means like you tilt. Yeah, tilt. So we are okay here, or?
Yep.
Yeah.
So
Is there other reasons to do dummies
yeah,
other than tilting?
yeah.
That's of diffusion.
The wall proximity is the one same as that. So when you have a well,
Well,
when you have a well to have the PMOSes, so the PMOSes, these are the PMOSes. They should be away from the border of the well. No, because here that thing is not okay. The and plot thing is not okay. So you are going to add dummies and make a distance. Also the same for NMOSes. Okay, this one is close to this bad area. This one is not. Okay, so you add dummies. Or I'm going to mention that, or you can do this instead of that. Both of them see very bad.
Or one on the right and one on the left, and they both see the
Yeah,
same well.
yeah, it's like that, you know, it's not like that, it's only like that. Instead of being like this, like this, like this. This is the well.
I was thinking if you have one transistor, the N well, and then another transistor on the other side, they will both see the N well, even if they're not close, so they won't be as well matched, but they will both see the N well.
Yeah, they both see that thing.
In your experience, how much dummy layers do you?
Never use dummies. Always do not care about that because it works.
depends on the technique. Let's say 1 micrometer.
1 micrometer away. Yeah.
This is the edge of the active region. Have to
1 micrometer. That was the difference. So 1 micrometer.
depends on your dummy.
You can find this thing on the some design
Yeah,
rules
the
or
explanation is the slides
oh,
that Conan sent you.
but it was the yeah,
It's for the LOD, for example.
it was 800 nanometer.
Depends on the technology, I would assume.
Yeah, but where you can find it because it should be documented.
It's hidden somewhere in the TSMC's shenanigans. It's well hidden. I looked for it for like maybe an hour yesterday before I found it.
Oh, you find something.
It's for 180 nanometers, so it's
What was
not at
the-
all the same thing.
What was the name of it? The name of the
It's a really long name with the letters and numbers that doesn't mean anything. It's TL009.65. I don't know the exact name. It's random numbers. You just need to find the right
It's
one.
like recommendations.
Yeah.
recommendation for the layout?
I think it's CLDR.
009 dash 2. My memory serves me right.
LDR is design rules, I think.
LDI?
CLD on the name of the document. I'm not sure.
It's always dependent on the techno, and when you use your DRC, it's this document that it's referenced to.
It will explain on the.
Yeah, you see a mistake in your what does it mean in this file?
28 and 65, I think. LDR, 2. 28 is CLDR.
48.
But for the LOD, for sure, if you have 5 microns of dummies, it is better than 2 microns or 1 micron. But I mean, after 1 micron, the effect will decrease for a reasonable ratio.
So because we are close to finish, I'm not talking about these parts like temperature and stress contours and gradient effects and concentrate the CP mix, yeah, kind of a target. And now I'm asking Conan about this poly spacing effect, length of diffusion, and OD to OD spacing effect. Are you there, Conan? Oh.
Yes, can you repeat that, please?
So we are not going to talk about the temperature and the stress of the contour, temperature and stress contour, and all of those things. We are going to skip that to go to these three that you kind of know about it. And you can share your screen to show us what is poly spacing effect, length of diffusion.
Okay, do you have the slide I sent you? You can share that.
Yeah, but the slide is not like if you talk about it, and it will be like if you draw something, draw something.
Les autres avaient accepté, puis je sais pas si le compte avait.
Okay, but I mean, this was to give.
Good.
Yeah, sorry. Okay. Yes, so I can request control here, request control. Okay.
Ah, parfait.
So okay, let's put that one here. So I think we all know that there is the lower you go into the process, and I mean the lower you go into the gate length and so on, the more you are dependent to your post layout effect. So to your layout itself. So there is some effect that are already known and are here even with higher or with older technology, but for the newer one, as when you start from 28 nano to, let's say, FinFET thing and so on, there is much more effect. But here is a short list of some of them. So I don't know if you talk about this one already. But I will not following. Yes.
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 Okay.
We
So
talked a little bit about length of diffusion.
okay. So this one, I
Okay.
mean,
Yeah, go ahead.
so this one here, I will give just very general knowledge about that. What that means is that, especially if we talk about matching here, so two device, let's say, okay, we discuss about the diff pair, right? So consider, imagine a diff pair. If
I
for
think if you draw something will be.
okay, so let me get down very quickly. I will do that and get back to my office. So je descends rapidement. Ça va être plus rapide pour tout le monde.
Ok, c'est bon.
Écoute, par exemple, si, mettons, c'est un gros appel de courant au démarrage, puis tu as trop de condensateurs sur ta sortie de ton power supply, il n'est pas capable de faire charger tous les condensateurs, fait qu'il shut down. Ça, c'est une des choses qui peut arriver.
No. Could we have those slides?
Yeah.
Yeah.
Maybe share it in the ASIC CAFE.
I will do that, yeah.
Nice.
So for the well proximity effect is and well.
Yeah, we talked about that, but I still do not know what is those other things and how we are
Yeah.
going to compensate for
Yeah,
that.
poly spacing effect in 28, for example. You see, you have a dummy.
Drawing is the thing.
Well, now we explain it.
Okay,
Did you work with 28?
a little, yeah,
The layout.
yeah.
In the transistor, there is always a dummy gate
Yeah.
already in the layout.
Yeah.
So I think this is the poly spacing. Each poly has to have a gate at 180 nanometers. For each
Tu sais de même? Je savais pas s'il y avait quelque chose.
We can do it all of them if you want. We can both have the slide and we can.
Peut-être tu peux projeter plus grand, tu peux dessiner dessus
lequel
le PowerPoint. Ah là, tu partages l'écran, mais c'est justement en ligne, c'est ça?
Ouais, pas mal. Sinon, il y avait. Ouais, de toute façon, il y avait juste toi, je te l'échelle.
Je partage le PowerPoint sur votre écran. Ah, c'est toi qui partages?
What should I do?
Can you just display the PowerPoint here instead of
Sure. It is fine.
I can go through all this very quickly. J'ai pas suivi au moins les échanges, là, j'étais occupé à plein d'autres choses.
on a parlé de LOP. Des exemples. Je demandais c'est quoi la raison.
Ok.
Bon, un micro.
Donc, on peut skipper ça. If you show this one,
This one.
the slide 3 here. Yeah, so the main thing to remember about the layer dependent thing is that when you have matching, when your matching is important, whatever is surrounding your device is important. You both need to see exactly the same thing.
Sorry, I think I'm not recording I should share the screen then.
Okay, you can share and go back to.
It's recording.
No,
He's talking about the screen, but it's only us right now. Everyone in the room, there's nobody online.
no, it's share or.
Yeah, well,
No, it's
Oh, to record, okay.
he wants to record the screen. Okay.
Okay. No, so whatever is surrounding your devices need to be ideally exactly the same to see the same effect, because
it's funny this here, but it's the reality. Whatever you said, hey, your well is messing my pressure voltage. So, because this is, so whatever is close to your device impacts its performance. Can be mechanical stress and so on. Usually it's mechanical stress, but it reflects an electrical difference between the two devices. So Next one. Yeah, next one. So this I already talked a bit I about think that. we already talked about what proximity. Okay, so you can go back maybe to the well. So this is one of the good explanation of why your well impacts the device, because you have a different structure here. So you're doping whatever is close to the well here, see a different doping than something far away here. And when you talk about matching, you want to have exactly the same thing for all your devices. So this is why for this result here, you need to have a certain space in between your real device and the edge, so the well here, to minimize this effect here. And this picture here shows an image, the difference of your threshold, the threshold versus how far are you from the edge. So the more far you are, so the less variation you have in your threshold. So this is why generally for the processes here and below, my experience at Cadence, for all the projects are working, the magic number was 1. You have to be below. We keep at least 1 micro to the edge for whatever device. Matching important or not, you need to have at least that. And even this, because usually when you make your simulation, your typical one or your standard one, the model suppose that you are far from the edge. So if you don't have this one into your real layout, you will see a real difference between your schematic and your layout, your post-layout simulation. And we saw that already. T28 is more important than
even 65. It's
for instance, less.
If you have like your device at the center and you have dummies all around, and then could you have like a space of no transistors for completing the 1 micron, or you fill that space with dummies?
For this rule, you will, as soon as you are far from the edge, even if there is no dummy, not an issue. It's okay because you are far from the edge, so you see this picture here, so you will not have this difference. But for over DRC rule, you cannot have empty space like this. This needs to be filled for uniformity, because you can have also some mismatch because of non-uniform expression of base layer or metal layer. This is why, I don't know if you already made the parts of the top design. But you usually at the end, before taking out, there is a fill script. You need to fill all whatever the space. You cannot have empty space to have. For some technology, for all the one, for example, 180, there was only global density. But the lower you go in the technology, you have local density. So for example, in an area of 5 by 5 micro, you need to have a certain density, minimum density.
Okay.
So yeah. So for this effect, no need to have dummy at the end, but for over thing, let's say, are we talking about the LOD thing? Need to have dummy.
But if you put dummies, will oblige you to.
Exactly.
So
Yeah.
dummy is your best friend. It's
Yeah.
a good practice.
I think it's enough with well proximity, but this one is the other one is very interesting.
This is
LOD and that other thing that you mentioned. Yeah. So this effect here is the same as the well we just talked about, but when you are not in a well, when you have your NMOS and so on, so at the edge here you have your STI, right? At its edge. So whatever
you don't have doping, you have another structure. You have some strength to isolate your device for the on the other substrates. So SI, I think, stands for shallow trench isolation, something like that. So the same thing as your well. So you can consider that one as an edge. In that case here, it's more a mechanical stress because I'm not going to the detail of the mechanical thing, but you have compression and extension of this makes some mechanical stress over the device. So strain and what's about look there, the strain and strain and so on. So the thing to sum up here is that those edge here create mechanical constraints on your device, and this affects its mobility. So because of this constraint here, if you have your device here at the center far from the edge here, see different constraints than the one that is here. So because of that, the mobility is different, and then the electrical performance are different also.
Those trenches are for like SOI or something. Not
Like
for-
I have to put something at the end of the talk.
Yeah, it's
Explain.
It's for SOI, I suppose it's not.
no, it's not for SY. It's the general CMOS processes. If you
Go
go in
back,
the
I think it's in the slide, the first slide. I think.
again.
Yeah, this one.
Yeah.
It is always
This
there.
is an SOI.
No, STI. This is not SY.
I know, but the technology you separate.
It's a piece of substrate.
This is
with a-
CMOS process. It's just something to isolate your devices, because if not, you will have some leakage, like some natural leakage. So wherever you don't have any active, with some device, you have some isolation like this.
So you should, what you should do is adding dummy. The compensation.
The dummy, if you go back again, So by adding dummy, you just add more space between the edge. I mean, it's the exact same thing as the well proximity effect. But now it's not the well because you are not in an end well, but you are in the substrate.
So if you add dummies, it's still, it will be STI.
You have to extend, the dummy will be,
The dummy here, this one will be your dummy, but then your real device here will be far from this STI.
But between dummy and the real device, it should be STI according to.
it has to be the same active region,
No.
a continuous
Exactly.
doping region.
Understand you, or
When you when you do when you add dummy, when you have some dummy, okay, let's say you have your real device here, and you have many fingers of this one. You have 25% so you have one device here. Let's say you have one device of 2 fingers, right? And then usually we have, I think all of you have made layouts. So you have this one, this is your active, right? It's not active.
you're talking about source membrane.
OT, yeah, OT. This is the OT layer,
Yes.
right? So this one, for all, for example, for LOD, when we talk about LOD, we talk about length of this diffusion. So you see what's the length of this one? This one, from one device to the end of this diffusion, this is called LOD.
Let's stay with STI, okay, then we are going to all of.
Yeah, I mean, I'm just explaining the fact that this one is a continuous area of thing.
So how do you add dummy? Is that-
The STI is always at the end of the OD region.
Okay, but when you add dummy, I know you can add dummy.
The dummy will be
But
inside.
dummy will be here. The dummy will be here. This is your real device.
Okay,
This one is your dummy.
so
Dummy.
That means
Oh.
you extend your LOD.
No, no,
exactly.
So
Put your
then
STI
merge
further
with
away
your-
from your real.
your-
Exactly.
These are dummy gates, not dummy transistor.
Can be done with transistor, but you will
If you
merge it
add
with the
more-
last.
You have
Source.
DRC problem if you add.
No, you will merge them. You have to merge the OD regions. You don't have to. The DRC rule is for ODs which are separated by the value.
Okay, okay.
You have-
So we kind of understand what is STI, thank you very much, but LOD, I think LOD will.
So the LOD, this is the definition of LOD.
Okay, how you compensate for that?
Okay, so
But what is the effect?
go
Like,
to the next slide.
oh, LOD is this thing, okay, okay. So it's not
STI is the layer,
Okay.
LOD is.
Thank you very much. So I think we
Okay,
covered.
okay, it's here. You get here, the definition is there. See, so the LOD, left, right, next is equal to LOD, okay. So exactly what I just said here. If you take one device, you look at how, where is the end of the OD layer, so the edge. So this is the L. If you take this one, the LOD that is seen for this device on the left side is that one, is that distance. If you look at on the right, it will be that one.
Thank you.
And this is the picture.
After mechanical, this is the contour of the stress.
Yeah, exactly. So the STI here, mechanically, I mean, the structure of the CMOS makes that you have mechanical stress on the edge. I mean, you have mechanical stress everywhere, in fact.
Yeah.
But if you look at the, look at here, you consider the two edge and you have, so the STI here and here. So there is more stress on the edge because they are closer to the STI, right? Yeah. But the more you come to the center, I mean, the more far you are, or the more extent you are. So the pattern of the stress is that it goes less and less and less. The far you are from the edge, the less stress you have. So if you consider, for example, that this one is your, okay, in both cases here, this is your device, the one you want to have. And those ones are just dummies. Those ones here are just dummies. So in that case below here, the stress, this one, see if you draw it without any dummies, and so that you will see this as stress. Because, I mean, just, il agresse et juste là. Voilà, juste là, donc il agresse, voilà le stress que lui il voit. Hey, sorry. So the stress is that high, and so the performance are, so the, for example, the PT, the pressure and so on change, the delta is very high. But because you put the dummies, so that you extend the LOD to minimize, so you enter, so the more, I mean, the longer your LOD, the less is your stress.
You will be
For example,
always.
here, in the case where you maybe have just two dummies on each side, it will still see the stress, but less than here. If you put more, even less stress will be there. And this is, if you go back to the other picture, by measurement, people discovered that usually after 1 micron, there is no point to put more.
Also, you mentioned this one, what is OD and PS?
This is a Foley spacing effect. So for example, if you have your diff pair, and when you do the layout, let's say this one A, this one B, if you do the layout of this one and you make everything match, I don't know, but for this one, the poly pitch, the pitch between the poly, let's say, is X, A, and you draw this one, but the poly pitch, you take a distance Y that is different from X, they will have different performance because the poly pitch is not the same. Because even if, I mean, as I said again, For matching what is surrounding your device impact its performance. So this one, there is a stress because you can see it as something, you can as a building or anything. So whatever is close affect or create some stress to its neighbor. So at this distance, X here, there is one amount of stress that everyone see. If it's different, it will be a different stress. So when matching matter, exactly to have the same thing to see the same stress. So poly spacing effect here is just a thing to say that, I mean, different spacing, you have
You mean when the
different
polys are away, so they have a problem? You are talking about this? Poly of two different transistors should be close to each other, not close, but not should be too much far away.
Not exactly that. It's your spacing, the spacing of between two poly has a different effect. So your spacing impacts the performance at the end that you have.
The spacing between two poly.
Between two poly, for example, here, if I draw this one and
Oh, this is two poly of two finger or?
yeah.
Oh,
That's two
So
fingers.
even if just parasitic, you can see that there is different impact because they are more close, there is more coupling, and even this is even worse with FinFETs.
so how should you solve that problem?
Just to keep the same spacing wherever, and usually this is what we do.
Okay, 28 it's years.
Yet there is some, but usually there is a range. You can, or discrete value, you can have.
28, we have the dummy poly.
Yeah.
Cannot change.
And what about the last one, OD to OD spacing, what is that?
OD to OD spacing, this was not something we care about very often. I mean, I didn't care about any of the project, but it's, if you have one device here that ends here and another one starting with OD that's starting here, so this spacing here also.
Isn't this
as
for your STI?
Exactly. I think all that is, they are all related to the
Yeah.
mechanical constraints due to the surroundings.
But if you have dummies, all of the four effects will be.
Yeah, so just adding dummy.
You have to pay attention. When you talk about dummies, they are not just dummies on the left and the right.
Yeah,
If
Top and
you-
bottom also.
Top and bottom, you have to be far from you when you have
also for
lots of diffusion.
for capacitors,
Yeah.
for capacitors, for the resistor, can use dummy.
Yeah. You must use.
You must
If
use.
matching is important, even
Yeah.
for capacitor,
Yeah,
for
for resistor, maybe it's not dope.
use you need like that. Because for resistor and capacitor and all those one you have the etching. And etching process, but maybe now is a different process for lower node, but when you have you have some that's CMP, chemical mechanical polishing, so and even some etching are dry, some etching are with chemical, and the surrounding there is some picture if you Google that, no, not in my slide here, but if you Google etching variation, because for that regarding etching, this is why for some process there are some there is dummy optical correction thing. Okay, so let's say if you draw even just your metallization, if you have, let's say, metal one like this, or one metal one like this in your card, in your layout, and you have another metal one, but having another metal one close here, this one and this one. after the fabrication, this one maybe will end up, I don't know. Je sais pas dans quel sens ça va aller là, mais lui, son etching, peut-être au final, là, ce que tu vas avoir, ça va être, bon là, je ne fais pas bien, là, ça va être comme ça. OK. Non, il ne sera pas plus gros là. Mais il sera arrondi, it will be, you will have something, okay, let's say, let's not interior, you will have that. Let me make it bigger. Okay, so if you have metal one like this, and you have same thing here, but with surrounding here. Post fabrication, maybe this one will give something like that. Post fabrication, you will get that one. But this one, because there is over metal close, and because of all the physical process of the etching, the mechanical polishing, and so on, this one is less of, I don't know. But the final shape of this one will be different from this one because of the constraint, technical constraint. If you apply a chemical thing, you will have less here because there is over constraint than here. So at the end, let's say, c'est pas la question ça va être plus ou moins, mais this one will be different. So for example, maybe it will be more etched than this one. So maybe this one will end like this. Just because of the stress, and the width for this one will be different from the width of this one.
So is it, do you want to have your metal further apart to be sure that you always have something that's uniform everywhere?
It doesn't matter,
Or
but
does it
if
really matter?
your matching is important, you need even the surrounding of your.
Okay, so
you
you-
to see the same. You see,
If you have an array of capacitors, you.
Yeah, okay.
Dummies,
Yes.
they
Yeah.
see the same.
because for example, the one on the edge will be more edge than the one on the. For example, if you have an array of capacitance and then you need, for example, it's I don't know, a DAC or something like that, and you have the bits 2, 4, and so on. So if you have this array here, so let's say you have a bit, oh, to say one example, you have 8, for example, here. This. Lost my encore.
The one in the center is.
The one in the center will be etched differently from here. So when you go to ×2, ×4, but you will not have the same multiplication. So you have some mismatch there.
It's
because
not
of
linear.
the matching.
We use also the center with the approach.
Exactly.
From my limited experience, I found that the one on the perimeter were more edged than
More
the
edged,
one
yeah.
at the center.
Because well, probably because they are more exposed to the
Yeah, well,
the
the
substance. that
CNT
they-
are not like really parallel and they have little angles, so
Mhm.
Maybe
the ones on the perimeter have more chemical etching and mechanical etching.
So this is why when you add those dummy all around, so they will be the one that is different and the one on the center will be more similar. So dummies go with matching. As soon as you want matching, dummies, whatever passive, active things, matching goes with dummies. Yeah.
Thank you very much.
Like that.
And